In this video, I'm going to introduce you to velocity vectors. So given a particle's position vector, which describes the path as the particle moves through time, given its position vector, you can actually obtain its velocity vector. Once you've got the velocity vector, what that means is it allows you to work out a particle's velocity as it moves through time. As it moves through time, you can work out its velocity. So let's say the particle is currently at time t, the particle is right here. And then after a certain amount of time, delta t, the particle will be right here. So the vector, the change delta r would be this thing here from here to here. So delta r would be this vector here. So how would you represent this vector here? You would need to go, remember, delta r at time t is right here. At time t plus delta t, the particle is here. So how would you travel from here to here? You would go back in the negative direction. That would be minus rt. And then you would go in the positive direction of the rt plus delta t. So delta r is given by you moving in the negative direction, hence the negative here, and then you would move in the positive direction here. That's why this is positive and this is negative. So delta r is from here to here. Okay, so hang on. So if you look at this, position here, this position would be given by this thing here, which is this thing here. So this is RT, and then this position here is given by t plus delta t. Remember, we are considering a delta t amount of time. Originally it was here. After a certain amount of time, the particle is here. So if you want to know the location at this point here, it would be f of t plus delta t, and then g t plus delta t. So you're putting t plus delta t into here, and then here you would put t plus delta t. And then this thing here would be t plus delta t. So this whole thing here would represent this location. So if you get this location, take away this location, then that will then give you delta r. So this delta r here really represents this, the vector from here to here. Okay, so delta r is given by this whole thing here, and then if you divide it by delta t, that will then give you the average speed. That would then give you the average speed. So divide the whole lot here by delta t. Well, dividing by the whole lot, you can just look at it. You can just look at each component individually. So looking at it in the x direction, divided by delta t, and then looking at it in the y direction, delta t, and then looking at it in the z direction, delta t. So that will then give us this thing here. The point here is that if you divide the whole lot by delta t, you can actually look at each one individually, each component individually. So let's look at it in the x direction, y direction, and z direction. Okay, so that will then take us to here, and then now take the limit as delta t tends to 0. Then that will then give us this thing here, and hopefully you can see that this thing here really is, well, when you take the limit as delta t tends to 0, it gives you the true gradient. So this thing here will then become this thing here will then become this, and then this thing here would then become this thing here. Hang on, this thing here is k hat, by the way. So that's this k hat here. So the derivative can also be written as this, by the way. So the point here is that if you want to work out the velocity, you can just differentiate this, differentiate the function f, differentiate the g, differentiate the h, and then that will then give you your velocity. Now, if you find if you find it hard to grasp why it is that you're able to look at it, if you find it hard to grasp why you're able to look at it in each component individually, because here we're looking at it in the x direction, in the y direction, and in the z direction. If you find it difficult to accept why you're able to look at the speed individually, well, let's just consider this. Hang on. Back in high school, you're able to accept this scenario here. Imagine a car traveling in a line. If you can travel 10 meters in 2 seconds, then you can say that, oh, the speed is 10 over 2 meters per second in the x direction. So you can accept this in high school. Let's say you've got a boat here traveling across a river and the water is flowing in this direction here. So let's say the boat is able to travel from here to here in 2 seconds. Then you can actually say, well, in the x direction, you've done 10 meters in 2 seconds. So you can say the speed is this amount of speed in the x direction, and then in the y direction, the speed in the y direction is 4 divided by, well, if you can do it in 2 seconds, then you can say the speed is 4 over 2 meters per second in the y direction. So here you're able to accept that you can do it in the x direction and then in the y direction. Let's say you've got a plane traveling from the origin to here, where it's 1, 6 across. So the coordinates here will be 1, 6, 5. Well, you can actually say the speed will be 1. Well, let's say the plane can do it in 2 seconds. Well, the speed will be 1 over 2 meters per second in the x direction, and along here in the y direction it will be 6. Well, you can do it in 2 seconds, so 6 divided by 2 in the y direction, and then in the z direction you can say 5 over 2 in the z direction. So the point is that you can look at the speed. Well, you can look at the speed by looking at its individual components. So in the x component, in the y component, in the z component, you can actually look at speed in terms of each individual component, x, y, and z. So going back to here, I hope you can accept that you can look at each one individually. So in the x direction, in the y direction, and in the z direction. Well, the velocity vector would be given by this thing here. So the point I'm trying to make is that given its position vector, given a particle's position vector, you can actually differentiate this, and then differentiate this. That will then give you its velocity vector. Okay, I will give you an example in the next video. Okay.